Hey everyone, and welcome back to the channel. Imagine a celestial canvas, vast and ancient, where the births and deaths of stars are meticulously plotted, their lives governed by predictable laws of physics, eons in the making. We understand the colossal forces that ignite them, the slow burn of nuclear fusion, and the dramatic final explosions that scatter their elements across the cosmos. But what if, one day, an anomaly shattered that understanding? What if, overnight, an object appeared in the sky, a beacon of light so intense, so sudden, so utterly without precedent, that it defied every stellar model we've ever conceived? An impossible star, born in a blink, blazing with an energy that should simply not exist, leaving astronomers scratching their heads and questioning the very fabric of the universe. This isn't science fiction. It's a cosmic mystery that unfolded just a few years ago, and it's rewriting the textbooks on stellar death. Get ready to dive into the enigma of the impossible star that just appeared. The year was 2018, and the astronomical community was largely going about its business. Telescopes around the world were diligently scanning the skies, cataloging new supernovae, tracking asteroids, and observing distant galaxies. Then, on June 16th, an automated survey telescope called Atlas, located in Hawaii, flagged something unusual. A new, incredibly bright object had appeared in a galaxy about 200 million light-years away, nestled in the constellation Hercules. Its official designation was at 2018 Cow, but it quickly became known by its more memorable, if slightly whimsical, nickname, the Cow. What started as a routine detection quickly escalated into a global astronomical emergency. The Cow was unlike anything astronomers had ever seen. Supernovae, the explosive deaths of massive stars, are common. Tidal disruption events, where a star gets torn apart by a black hole, are also known. But the Cow defied easy classification, exhibiting characteristics that simply didn't fit into any established box. First, its speed. From being completely undetectable to reaching peak brightness, the Cow took just a few days. For comparison, most supernovae take weeks to reach their maximum luminosity. This rapid rise indicated an incredibly powerful and compact source, unleashing energy with almost unheard-of efficiency. Then it faded almost as quickly, before settling into a more complex, fluctuating decline. This speed was paradoxical. Immense energy usually takes time to diffuse and become visible. The Cow was like a cosmic flashbulb, an incredibly bright, incredibly fast burst. Second, its brightness. At its peak, the Cow was astonishingly luminous, shining with an absolute magnitude of around -20. This put it in the same league as some of the brightest supernovae ever observed, despite its incredibly short lifespan. The sheer amount of energy released in such a short period was mind-boggling, far exceeding what conventional models of stellar explosions predicted. Third, its spectral signature. When astronomers analyzed the light from the Cow, they found another puzzling characteristic, a near-total absence of hydrogen and helium lines. These elements are the most abundant in the universe, and their presence is a hallmark of most supernovae. Their absence in the Cow's spectrum suggested either a progenitor star that had already shed these outer layers before its catastrophic end, or an explosion mechanism so fundamentally different that it bypassed these usual signatures entirely. It was blue, indicating extreme temperatures, but the elements making up this incredibly hot plasma were mysterious. Finally, and perhaps most tellingly, its multi-wavelength emission. While most celestial objects emit predominantly in one or two parts of the electromagnetic spectrum, the Cow blazed across the board. It was incredibly bright in optical light, but also emitted powerful X-rays and radio waves, especially in its early stages. The X-ray emission, in particular, was exceptional, far more intense than what's typically seen from supernovae. This complex and energetic multi-wavelength profile screamed unique and unprecedented. The news of the Cow spread like wildfire through the astronomy community. Observatories around the globe, from ground-based radio telescopes like the Carl G. Jansky Very Large Array, VLA, in New Mexico, to orbiting X-ray observatories like NASA's Chandra and NuSTAR, and even the venerable Hubble Space Telescope, quickly pivoted to observe this cosmic enigma. The goal was simple: gather as much data as possible across the electromagnetic spectrum before the Cow faded into the background, taking its secrets with it. This was a true astronomical detective story unfolding in real time, with dozens of research teams worldwide pooling their data and expertise. Hubble's sharp eyes helped pinpoint the Cow's exact location within its host galaxy, CGCG 137-68. It wasn't in the galactic core, where supermassive black holes reside, but rather in a relatively quiet, off-center region. This location ruled out some typical scenarios, adding another layer of mystery. As the data poured in, theoretical astrophysicists began to formulate hypotheses, each more exotic than the last, trying to explain this impossible star. Three main categories of explanation quickly emerged, each attempting to reconcile the Cow's unprecedented speed, brightness, and unusual spectrum. One leading idea was that the cow represented a failed supernova from a very massive star, perhaps 10 to 20 times the mass of our sun. In a typical supernova, the core of a massive star collapses, creating a shockwave that blasts the entire star apart. But what if, in this instance, the collapse was so rapid and powerful that it formed a black hole, and most of the stellar material fell back onto it? This fallback accretion could launch powerful jets or winds, ejecting a small amount of material at incredible speeds and heating it to extreme temperatures. This scenario could explain the rapid burst of energy and the intense X-ray emission. Lack of hydrogen and helium would then imply that the progenitor star was a specific type, like a Wolf-Rayet star, which sheds its outer hydrogen/helium layers before collapsing. The rapid infall of matter onto the newly formed black hole would efficiently convert gravitational energy into radiation, creating the observed flash. Another strong contender was a tidal disruption event, TDE, caused by an intermediate mass black hole, IMBH. TDEs occur when a star ventures too close to a black hole and gets ripped apart by its immense gravitational tides. The shredded stellar material then forms an accretion disk around the black hole, heating up to millions of degrees and emitting intense radiation, particularly in X-rays. What made the cow a unique candidate for a TDE was its speed and its location. Most known TDEs involve supermassive black holes at the centers of galaxies and can last for months or even years. The cow was far too fast and not in a galactic center. This led to the intriguing hypothesis of an IMBH, a black hole weighing hundreds to tens of thousands of solar masses, bridging the gap between stellar mass black holes and supermassive ones. If a smaller star, perhaps even a white dwarf, the remnant of a sun-like star, was devoured by an IMBH, it could produce a shorter, brighter flash like the cow. The white dwarf, being primarily carbon and oxygen, would also explain the absence of hydrogen and helium in the spectrum. The rapid consumption of a compact object by an intermediate-sized black hole would provide the exact conditions for such a super-fast, super-bright, multi-wavelength flare. A third, more exotic possibility considered was the birth of a magnetar. A magnetar is an incredibly dense, rapidly spinning neutron star with an extraordinarily powerful magnetic field, a quadrillion times stronger than Earth's. The formation of such an object from a massive star's collapse could release immense rotational energy, which could then be siphoned off and converted into electromagnetic radiation. This could account for the rapid energy release, but the total energy output of the cow seemed to exceed what a standard magnetar could produce, leading most researchers to favor the black hole-driven scenarios. As the observational campaign continued, critical pieces of evidence emerged. Radio observations from the VLA were particularly revealing. They showed persistent radio emission from the cow, indicating an expanding, relativistically moving jet or outflow of material. This was a very strong indicator of a powerful, compact central engine, something like a black hole violently interacting with matter. The outflow was incredibly fast, moving at a significant fraction of the speed of light. Meanwhile, X-ray observations from Chandra and New Star confirmed the extreme temperatures and, more importantly, showed a power law component in the X-ray spectrum, which is characteristic of accretion onto a black hole. They even hinted at rapid oscillations, almost a heartbeat, which could be the signature of a compact object spinning or accreting material in a specific, rhythmic way. The combined evidence gradually tilted the scales towards the black hole hypotheses. Currently, the most favored explanations revolve around a central engine powered by a black hole. Either a newly born black hole rapidly accreting fallback material from a massive, hydrogen-poor star and launching powerful jets, or an intermediate-mass black hole tidally disrupting and consuming a white dwarf star. Both scenarios elegantly explain the key features: the extreme brightness, the rapid rise and fall, the lack of hydrogen/helium, and the powerful multi-wavelength emissions including high-energy X-rays and relativistic radio jets. The challenge now is to definitively distinguish between these two compelling narratives, a task that remains incredibly difficult given the vast distances and the inherent ambiguities of cosmic events. The cow, the impossible star that just appeared, has profoundly impacted our understanding of the universe. It serves as a stark reminder that the cosmos is far more dynamic, violent, and full of surprises than we often assume. Firstly, it has forced astronomers to challenge and expand their paradigms of stellar death. Supernovae are no longer a monolithic category. The cow demonstrated that there's a whole spectrum of extreme transient events that defy traditional classification. It pushes us to broaden our understanding of how massive stars end their lives and what happens when compact objects, like black holes, violently interact with other stellar bodies. It reveals that nature has more than one way to end a star's life with a spectacular bang. Secondly, if the cow was indeed a TDE by an intermediate-mass black hole, it provides tantalizing observational evidence for these elusive objects. IMBHs are considered missing links in black hole evolution, bridging the gap between the stellar mass black holes, formed from collapsed stars, and the supermassive black holes that reside at the centers of galaxies. Finding and studying them is crucial for understanding how black holes grow over cosmic time and how they influence the evolution of galaxies. The cow offers a rare glimpse into their potential existence and behavior. Thirdly, the incredible energies and exotic physics involved in events like the cow push the very boundaries of our understanding of high-energy astrophysics. Mechanisms for launching relativistic jets, the rapid heating of matter to millions of degrees, and the highly efficient conversion of gravitational energy into electromagnetic radiation. These are all areas where events like the cow provide invaluable real-world data, allowing theoretical models to be tested and refined. They serve as natural laboratories for extreme physics that we can only dream of replicating on Earth. Finally, the cow underscored the critical importance of rapid, all-sky astronomical surveys. Telescopes like ATLAS, the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSSD, at the Vera C. Rubin Observatory are designed precisely to catch these kinds of fast-evolving, unexpected transients. Every night, these robotic sentinels scan the sky, waiting for the next impossible star to appear, ready to alert the global astronomical community to a new mystery unfolding. The universe is a constantly changing canvas, and these observatories are our eyes, ensuring we don't miss the next cosmic drama. While AT2018 COW has given us immense data and fueled countless studies, it hasn't been definitively solved in the sense of absolute consensus. Leading theories are robust, but distinguishing between a newborn black hole with fallback accretion and an IMBH devouring a white dwarf is incredibly difficult with current data. Both have compelling arguments and fit many of the observations. Astronomers are actively searching for cow-like transients, and a few candidates have since been found, showing similar rapid rise times and extreme luminosities, but none have perfectly matched the cow's unique fingerprint. Each new discovery helps to refine our models and narrow down the possibilities. The study of these impossible stars is a testament to the ever-evolving nature of science. What seems impossible today often becomes the catalyst for new discoveries and a deeper understanding tomorrow. These events are not glitches, they are signposts to the unexplored territories of astrophysics. They remind us that our cosmic neighborhood is anything but static, constantly surprising us with phenomena that push the very limits of our imagination and our physics. And as we gaze at these cosmic enigmas, we're reminded that the universe always holds secrets far stranger and more spectacular than we can possibly imagine, waiting to burst into existence right before our eyes. Thanks for watching. Please subscribe my YouTube channel for more interesting videos.